time to move on to multi-electron atoms. And we're going to start here with helium. Well, the Schrodinger equation, of course, correctly predicts the atomic structure of all atoms, right? But the difficulty is that as you increase the number of electrons, the problem, the differential equation that you have to solve gets more and more complicated. And there is no nice analytical way to solve that equation, which means that there's not going to be a nice analytical form, for example, for the allowed energies of a helium atom. That is, we're not going to get an expression of E sub n equal to minus R sub h over n squared. This is a nice analytical expression for the hydrogen atom energies. We're not going to get that for helium. All right? So if you solve the equation for helium, what you actually have to do numerically, what you're going to get is a list of numbers. And you're not going to get a nice analytical form for the wave function. What you're going to get is the amplitude of the function as a function of r, theta, and phi, another list of numbers. Okay? But the truth is, as you increase the number of electrons in the system, you very quickly, by the time you get to 3 and 4, run into such a problem that you can't even solve the Schrodinger equation exactly, even numerically. Okay? Why? Well, here's the example. Here's helium. Here's the Schrodinger equation for helium. I didn't write out the Hamiltonian precisely. I just wrote it the general Hamiltonian. But what I want you to see is that the true wave function for the helium atom would be a wave function that had 6 coordinates in it. 2 values of r for each one of the electrons, electron 1, electron 2. 2 values of theta, 2 values of phi. Hey, we already have 6 coordinates in that wave function in the case of helium. And as we go to lithium, beryllium, boron, hey, the number of electrons, these wave functions, the number of coordinates, it just goes up exponentially.